take it away.
So, should I go?
Yep, sorry, go ahead.
Okay, great. Well, hi everyone. Thank you very much for having me. Thank you to the organizers. I'm really sorry to not have made it in person. So I am a new postdoc starting to work with Marcy Robertson very soon. Marcy, who told you earlier today about CV. And unfortunately, I still don't have my visa to come to Australia. So it's a small consolation to be able at least to give this talk, and I'm looking forward to in-person interactions. So the product I'm going to talk about today, it's a common project with Pierre-Louis Curien. Our starting point was the following quote from the starting point was an article of Kapranov, and in this article, this is from the introduction of a 1993 paper by Kapranov, and he says, so maybe the most important is the two last sentences. So he says, we shall construct Kpn as a CW complex in section 2 and show that it is an n-1 ball. This gives an instant one-step proof of MacLane's theorem in full generality. And we were quite impressed by this statement. We wanted basically to know what was this one-step proof of MacLane's coherence theorem. And well, here, what is Kpn? So it's basically a CW complex, at least in Kapranov's paper, where vertices are in bijection with full parametrizations of the different permutations. So I have some, since then it has really been realized as a polytope. And so for permutations of 3 letters, you get this beautiful two-dimensional polytope here, which is called the permuto-associahedron. And in 3 dimension, you get this beautiful polytope, which has over 100 vertices. So this was the initial motivation. So let's start with the what is MacLane's coherence theorem from the start. So we start with a set, and then we define a syntax. So we use so these definitions are recursive. So the object terms, it's all the elements of A, and also tensors of elements of A or previous elements that you've already made. So tensors of tensors. And then you also have morphism terms, which are named alpha or alpha -1. You can compose them, you have the identity, and you can also tensor them together. And you specify typing rules, which is to say, so a typing rule, for those who are not familiar with type theory, I am not an expert of type theory either. Pierre-Louis is. This is why we need to collaborate. But basically, these fractions mean that whenever the statement on the top holds, then on the denominator on the top, yes, then the statement on the denominator also holds. And in this case, there's nothing on the top, so we just say that what is on the denominator holds, and it is the associativity relation, and it's given by the morphism term alpha. So there's also the alpha -1, which goes in the other direction, moving the parentheses from right to left. You have the identity, and you have the typing rules that are relative to composition and also tensoring morphisms together. So now we define free of A, which is this syntax, but where we quotient the morphism terms by the laws of categories and bifunctors, and also by Maclane's pentagon equation. So it is the fact that this diagram commutes. Now what we obtain when we do this, we obtain the free monoidal category over A. So that is to say, a category that possesses the following universal property, that if you take any monoidal category C and any function from A to the objects of C, then you have a unique strict monoidal functor from free of A to C, which extends rho. Then we will denote this functor by double bracket. So now we're ready to state Maclane's coherence theorem. So it says that for any two parallel morphisms in free of A, for any monoidal category and any valuation, these two morphisms are equal under this strict monoidal functor. So maybe how do we go on to prove such a theorem? So we will simplify a little bit the statement by defining a syntax of basic context. This means that it's a all, like the first one, it's a bracket, it's a all which can be filled in, and then you can from a previous context, then you can tensor it with identity on both sides. And so what it says, it's just maybe a convenient notation for something like this morphism here. So where you apply the alpha only in the middle of an expression, then you can translate this into I just evaluate alpha in a certain context. And so we will use, you can use then the notation that is below, which is much shorter and much more clear conceptually. Now, the small lemma. So if you look at every morphism term in free monoidal category on A, it is a formal composite of canonical isomorphisms in context. So canonical iso here is the alpha and alpha minus 1. And it's a simple consequence of the fact that we've imposed functoriality. So since you have functoriality, then anytime you have a morphism, you can decompose it in the different elementary canonical morphism and write it like this. So now we're reduced to a statement, the coherence theorem. Now we're interested in comparing parallel paths between objects terms. So now we will say that two parallel paths, that is two morphisms that have the same source and same target, they are elementary homotopic if they differ only on either a square or a pentagon. And we will say moreover that they are homotopic if they are related by a finite number of elementary homotopies. And now we can state the following theorem. So any two parallel paths in the free monoidal category on A are homotopic. And this is actually from this is actually the core of the coherence theorem, because once you have this, then you can prove Maclane's coherence theorem. And it's not really difficult. So first you need two small lemmas. So the first one says that if the pentagon commutes in all empty contexts, that is, for only words of with 3 letters, no, 4 letters, sorry, then it holds in any context. And this is again a direct consequence of functoriality that we have imposed. And then the second lemma is that if the pentagon commutes, then any pair of parallel paths in it also commute. And the way to see that, so this is not very difficult either. Ooh. Yeah, let me put some color in. So if you look at a different path, so for instance this path here, then since you have canonical isomorphisms, you know that this path will be equal to this other path. So this is also a very simple lemma. And now from the theorem, so knowing that 2 parallel paths are homotopic, then we get a finite number of elementary homotopies between M and M prime. And using these 2 lemmas, then we get that evaluated on this unique strict monoidal functor, every pair of paths are equal, and thus the first and the last path are also. So with this theorem, it is fairly easy to prove the coherence theorem. But now the question is, how do we go on in proving this theorem, that any 2 parallel paths in the free modal category are homotopic? And this is where the polytopes enter the picture. So we will be interested in polytopes. And what is a polytope? A polytope, it's the convex hull of a finite set of points in Rn. So if you take, I don't know, these points, then you take the convex hull, and then you get a polytope. And so a polytope has, as you can see, 0 faces that are the vertices, 1 faces that are the edges, and then this one has a 2 face in the middle. Let me find a nice 3-dimensional polytope. If you have you can see what a 3-dimensional polytope looks like. And now we will say that a path on a polytope will be the cellular image of a continuous cellular and injective map from the interval to P, or we can also say from the unique 1-dimensional polytope to P. So it's something that will look like this. So if I take this 3-dimensional polytope, then a path, it will be a sequence of vertices and edges that are at each step adjacent. So this, for instance, could be an image of gamma. Now, remark that if you look at a 2-dimensional polytope and you look at the path on a 2-dimensional polytope, so they pick up 2 vertices and then you look at 1 path between the 2, then there is a unique complementary path which is parallel in the sense that it has the same value on 0 and on 1. So they are both paths between these 2 extreme vertices. Now we will make a very analogous definition to what we said before. So we'll say that 2 paths on a polytope are elementary homotopic if they differ only on the 2 face of P. And we will say that they are homotopic if they are related by a finite number of elementary homotopies. Now, we need another construction that you can do or perform on a polytope. And so what you will do is you will look at a polytope, pick up a vertex, and then intersect the polytope with the hyperplane in general position very close to that vertex. So you will obtain something that looks like this. Here, so you have your vertex V over here. Oh, sorry. Here you have your vertex V, and then you have the hyperplane H, this hyperplane here, and you intersect the polytope P very close to V. And what actually you get another polytope of dimension 1 less, and whose so k-1 faces are in bijection with the k faces of P, which contain V. So for instance, the one face here in the vertex figure corresponds to this two face here, which contains V in P. So you have P here, and you have, here P, the vertex figure, it's a one-dimensional polytope. It goes like this. So maybe I should have taken different colors. So, and yeah, and this is the two face corresponding to the one face in the vertex figure. And so now we can state the polytopal coherence theorem, which and it says that any two parallel paths on a polytope are homotopic. And then how do we go on proving that? So you look at two parallel paths on your polytope, gamma and gamma prime, that go, you take V, one of the endpoints, common endpoint to the two paths, and you take E and E prime, the two edges that are that belong to gamma and gamma prime and which contain V. And now you define M and N. So M will be the maximal length of a path parallel to gamma and gamma prime in P. And N will be the maximal length of a path between E and E prime in the vertex figure of P at the vertex V. So imagine that there are others edges here that go out of V, and then you cut with an hyperplane, and then E and E prime become vertices of this new polytope. So now to prove the theorem, we proceed by lexicographic induction on this pair M and N. So if the first case is that if E is equal to E prime, then we can consider the two paths, gamma and gamma prime, but removing this edge, and we can apply induction on the first factor, so to M. And if E is different from E prime, then you consider a path of minimal length between E and E prime in the vertex figure. You look at the corresponding family of two faces on P, and then you intersect gamma with this family F of two faces, and on the first two face you can switch gamma to gamma up on this two face, because there's only one gamma up, and then you can apply induction on this new path that you obtain by switching gamma 1 to gamma 1 up, because you've reduced the distance between E and E prime in the vertex figure. So this completes the proof. Now, why is this theorem on polytopes important to us? Is that because now you can prove the analogous statement. It implies the analogous statement in the context of monoidal categories because of this surprising, maybe this fact that is maybe surprising, that the syntax that we have defined with objects and morphism terms, it corresponds exactly to the one skeleton of a family of polytopes, which are called the associaedra. And so these are the first 3 associaedra. So for every, so one combinatorial description of associaedra is that the faces are in bijection with planar trees with a fixed number of leaves, but equivalently, the faces are in bijection with parenthesized words with a fixed length. So the theorem follows from this fact and the second fact, which is a remarkable property of these polytopes, is that all their 2 faces are either squares or pentagons. So this is why in the coherence theorem you can ask only the pentagon to commute, and then it implies that every diagram commutes. So a few remarks. So I presented only the case of non-unital, non-symmetric monoidal categories. And of course, you want to treat the case of symmetric monoidal categories, and in this case, you can apply exactly this reasoning to the permuto-association, which I presented at the very beginning, and which was introduced by Kapranov. Now, if you want unital symmetric monoidal categories, unfortunately, it's not encoded by polytopes anymore, but there are CW complexes, which are called unital associaedra, which were introduced by Muro and Tonks, but you would have to use slightly different techniques because these are not CW balls. And so, yeah, of course, you can ask the original question of Kapranov, and does this apply to every CW ball? This is something we're still investigating. So you can think of.
I'm sorry to interrupt.
Yeah, go ahead.
We're about out of time. Sorry.
Okay, sure. Let's end here. No problem. Yeah, that's great. So you can, this theorem, since it applies to a polytope, it can be applied to many other polytopes as well, which encode other interesting algebraic structures and categorified structures. That's it. I will be happy to answer questions.